we have a numerical method that helps us finding a solution, an approximate solution, we want to know how bad of an approximation we're doing. This is called error analysis. So we're looking at finding the approximation error that we're doing when we're doing the approximation. So let's look at the difference between the first step taken by our Euler method and the first step taken exactly. The difference between these two terms is the Taylor remainder term. The Taylor remainder term that is bounded by the second derivative of x computed at some value xi divided by 2 multiplied by h2, where we can write the second derivative of x as partial derivative of f, so we have a good handle of it. But the key element here is that we are multiplying something that we could compute that is given by the ODE times h squared. This is the error. This is the error that we're doing at each step that we're doing our Euler method. So the smaller h goes, the smaller the step, the smaller the error that you're doing in that step is. So we know that the difference between x at h minus x1, that is our numerical approximation for x at h, is of the order of h squared. What about x at time t? So I'm interested in looking at the solution after a certain time. We've fixed the time t, and we can choose to increase or decrease h. But if we decrease h, the number of steps that we need to get to t increases, and every single step gives us a bit of an error. So how does this work? How does it work out? Do we get better results if h is small at the end of the day? Actually, we do, because if we're thinking about it, then at the last step, you have accumulated all the errors of the previous step. So you can say that the error at time t, the difference between xt minus xn, where xn is the approximation of time t, is bounded by a sum of all the errors that you're done at every turn. That is O of h squared. I assume you know big O notation. If that is not a problem, write in the discussion and I'll do a video about it. Where h squared, an error of the order h squared, is given at every step. But we're summing from 1 to n, where n is given by the final time divided by h. So we know how many times we are summing this. We're summing by a constant times 1 over h. So our error is 1 over h times h squared, that is h. Sorry. This means we call methods in which the error at time t is of order h at power 1 first order methods. First order methods really refer to the fact that the error grows or decreases as the step size. Let's go into second order methods. That means that we want the error to be more precise. A first order method means that the error between the approximation at times t and the exact value at times t is roughly h. So when we halve the step size, the error is also halved. But the number of computation is doubled. So we can do more computations to get a more precise outcome, but the ratio between doing more computations and getting a better outcome is quite poor. We'd like to get something of second order. We want the error at times t to be roughly h squared. For that, we need the error at the first step to be h3. So we can take again our Taylor series and decide to go one step further, but there are elements that we don't know. In the sense, we could know if we by hand compute f prime, but a computer would not easily be able to do that. So we have to find another way. Instead of considering two elements, x, xn, and x plus 1, n, we now consider 3 points, xn minus 1, xn, and then xn plus 1, each of them being an approximation. And we would like to write an approximation of xn minus 1 and xn plus 1 as if we knew xn. So in both cases, we use the Taylor series up to order 3. And then we make the difference between the two values. So we have now xn plus 1 minus xn minus 1. And you notice that if we're taking the difference, then xn and xn cancel out, and the second derivative of xn that we cannot compute also cancels out. So we retrieve something that depends only on x dot n, that is something we could know, we can use the ODE to know, and nothing else. And the error is OH3, so this is a second order method as we wanted. We can write it down, and we have that xn plus 1 is equal to xn minus 1 plus something computed at xn. But remember, xn is the middle point between xn plus 1 and xn minus 1. We don't, if we know xn minus 1 and we need to know xn plus 1, we need xn. But xn is the middle point between the two. So we need to know xn plus 1 in order to compute xn. This sort of loop that you need both elements is called, it makes this method called implicit. It's still possible to solve it, but it's not as straightforward as the Euler method that we have seen before. So let's look a little bit at how you can solve this. You can either set xn plus 2 equal xn plus f computed at xn plus 1 times 2h. And in this case, we are considering that we know xn plus 1, but we have to find out xn plus 1 via a different method. Or at each iteration, we solve this problem that aims to find both xn plus 2 and xn plus 1. And this is a nonlinear problem, but it's a zero finding problem, so we know how to solve these things, also numerically. These methods that I have presented are part of the broader category called Runge-Kutta methods. There are many of them, and I want to present one more. We can say that what we have introduced before, we have f computed at xn plus 1. We can say that that is just the approximation, the average between f computed at xn and f computed at xn plus 2. So we retrieve another method, another second order method, but that doesn't depend on xn plus 1 anymore. It only depends on the endpoints. This is to give the idea that there are a lot of possible ways to make the approximations, and each of these ways could be legit. Runge-Kutta methods are a broad category of methods that have a nice format to tell you what possible ways you have to get the approximations. I don't want you to learn the definition of Runge-Kutta by heart. The idea is that each Runge-Kutta method is defined by these values b, a, and c. And the idea is that xn plus 1 is equal to xn plus a bunch of terms that are value of the slope at some middle steps between xn and xn plus 1. Runge-Kutta methods are extremely broad. There are a lot of them, and there is a lot of interesting research going on in there. But this is my main point in here is they exist and they're extremely flexible.